Namaskar. So today we have the topic which is much awaited by most of the students. They asked me when you upload this topic. So today your wait is over. So don't worry. Today we will study Henry's law. This is very important topic. Keep in mind. And when we see the effect of pressure on the solubility of solid in liquid, there is very less effect on the solubility of solid in liquid as far as pressure is concerned. But when we see the solubility of gas in liquid, pressure has very significant effect, because when we increase the pressure, then what happened? Number of gas molecules per unit volume increases, and as number of gas molecules per unit volume increases, the number of collision of the gas molecules with the surface of the liquid goes on increasing, and that's why more gas is dissolved in the liquid. And this effect is quantitatively studied by William Henry. That's why that is called Henry's law. We can say it pictorially. Let us take 3 containers. Of the same size. There is liquid inside, same amount of liquid and same amount of gas. Let us take same amount of gas above the liquid. It is closed container. There is a piston. Now when we have piston and there is a weight on it, that means this is atmospheric pressure. Pressure increases more, it is more than atmospheric pressure, and if we increase further, more weight is above the piston, then piston is moved toward the liquid, and that's why number of gas molecules per unit volume increases. As number of gas molecules per unit volume increases, more gas molecules are in the liquid. तो क्या हो रहा है? If we increase the weight over the piston, what happened? Piston comes towards the liquid, and in that way, जो gas molecules है, these gas molecules, they more collide with the surface of the liquid, they more interact with the liquid, and more gas molecules enter the liquid. That means solubility of the gas increases as the pressure above the liquid increases. So that is what Henry's law is. So first definition of Henry's law. There are total 4 definitions of Henry's law. Keep in mind. Just first definition, according to Henry's law, mass of gas dissolved in unit volume of liquid is proportional to pressure of the gas above the liquid, or we can say in equilibrium with the liquid. So mathematically it is mass is proportional to pressure, or we can say mass is equal to Henry's constant into pressure, right? See, m is mass of the gas dissolved per unit volume of the liquid, this is m, and P is the pressure in equilibrium with the liquid or above the liquid. As pressure increases, more gas molecules enter into the liquid. That means solubility of the gas in the liquid increases, right? Now this KH is called proportionality constant or Henry's law constant, or simply Henry's constant. And this Henry's constant depends on, its value depends on, first it depends on nature of gas, it depends on temperature, it is at a given temperature, or it also depends on units in which pressure is measured, right? Because as unit of pressure changes, the unit of KH also changes, right? So note down this part. So nature of the gas as well as nature of the solvent, temperature and units in which pressure is measured. So note down this part, then we will proceed for second definition. Now second definition, so as per second definition, solubility of a gas in liquid at constant temperature is directly proportional to the pressure of the gas in equilibrium with the liquid at that temperature. This is the second definition. Now say, according to this definition, solubility of a gas in a liquid is proportional to pressure of the gas in equilibrium with the liquid. Now at the same time, Dalton independently see and found that solubility of a gas, if there is a mixture of gases, then solubility of each gas is proportional to the partial pressure of the gas in the equilibrium with the liquid. That means each gas is soluble in the liquid as per its partial pressure. And then Henry's law is restated as that mole fraction of the gas, let us take A as the gas, mole fraction of gas A in the solution mixture is proportional to partial pressure of the same gas in equilibrium with the liquid. That implies XA equal to KHPA. So first part is M equal to KHP. Second is XA equal to KHPA. Now see here, KH, XA is dimensionless, you know, PA is pressure. So KH, unit of KH is either per bar or per atmosphere, the way pressure is measured. If pressure is measured in bar, then unit of KH is per bar. If pressure is measured in atmosphere, then unit of KH is per atmosphere. So it depends upon the unit of KH that which mathematical operation is used. If KH is in per bar or per atmosphere, then Henry's law is XA equal to KHPA. And third definition is, this is the most common, Henry's law most common definition is partial pressure of gas, any gas, in equilibrium with the solution or liquid is proportional to the mole fraction of gas in solution. See, partial pressure of gas in equilibrium with the liquid, that means, it is above the liquid, that is in vapor phase. Partial pressure of the gas above the liquid in equilibrium with the liquid is proportional to mole fraction of the gas in solution at a given temperature. This is the most common definition of Henry's law. So according to this, PA equal to KHXA. This is third equation, and it is used when KH has units in terms of bar or atmosphere. So if KH is measured in bar or atmosphere, then we use this relation. If KH is measured in per bar per atmosphere, its units are per bar per atmosphere, then we use this equation. Okay. If KH is in, tell me, gram per atmosphere, gram per bar, okay, then we use first relation. Okay, so these are the three definitions, just note down. So far we have derived three relations for Henry's law. First is M is equal to KHP. This relation is used when KH is in gram per bar or gram per atmosphere, right? Second relation is used, that is XA equal to KH PA. It is used when we have mixture of gases. Then XA is mole fraction of gas A, PA is partial pressure of the gas in equilibrium with the liquid. Then when it is used, when if pH is in per bar or per atmosphere or kilobar per kilobar or per atmosphere, or third relation, that is PA equal to KHXA. That is most common and it is used if KH is in bar or atmosphere. Right? Now, last one, fourth one. If we measure the solubility in terms of volume of the gas, let us take this relation. M is m gram of gas. Let us take as volume VCC at temperature, at pressure T. Let us take this relation, that m gram of gas has volume V cubic centimeter at pressure P atmosphere. Right? Now let us increase the pressure. Let us increase the pressure is increased to 2P. If we increase the pressure, then what happened? Mass of the gas dissolved in the liquid is 2m, because when we increase the pressure, more gas is dissolved and mass and pressure are directly proportional. So as pressure is doubled, mass dissolved is also doubled. Now what about the volume? So now volume of the gas dissolved is 2V measured at pressure P. Keep in mind, if we measure the pressure in P, because at pressure P volume dissolved is V, and if we increase the pressure, volume dissolved is doubled, but that pressure, that volume should be measured at pressure P, then it is doubled. But what happened when pressure is increased? Then volume is decreased as per Boyle's law at constant temperature, because all the relations are at constant temperature. So, and pressure and volume are inversely proportional. So in this way, this volume is, when volume pressure is doubled, pressure is 2P, then volume of the gas dissolved is halved. So it is half of 2V, that is VCC. That means volume of the gas dissolved, see, mass of the gas dissolved is doubled, but volume of the gas dissolved at constant temperature in the liquid is independent of pressure. This is the last definition of Henry's law, that volume of gas dissolved in given volume of liquid at constant temperature is independent of pressure. Because when we double the pressure even, then volume of the gas dissolved is same. So we can say the volume of the gas dissolved in a given volume of liquid at constant temperature is independent of pressure. These are the four definitions, but most commonly used mathematical statement of Henry's law is this one. Most of the questions are solved by this. But you see, if kH is in bar and atmosphere, then only it is used. If unit of kH is per bar or per atmosphere, then we use this relation. If kH is in gram per bar or gram per atmosphere, then we use this relation. All the relation can be used, and this is the simple statement of the Henry's law. So as far as your competitive exam is concerned, you should note down all the things, all the definitions, right? But as far as your school exam, NCERT is concerned, this and first and third is sufficient. But we cannot rule out this definition, because sometime kH is given in per bar per atmosphere, then we should use this one. That's why I write that kH depends on nature of the gas and solvent, temperature, and third is unit in which kH is measured, right? The unit of kH is very, very important as far as mathematical statement of Henry's law is concerned. Otherwise, these two statements can be easily defined, that partial pressure of the gas above the liquid in equilibrium with the liquid is directly proportional to mole fraction of the gas in the solution. Okay, so both the definitions are covered. And if we plot a graph between partial pressure of the gas or we can say equilibrium pressure and mole fraction of the gas, so what is the nature of the graph? See, when XA is 0, PA is 0. When XA increases, PA increases accordingly. So graph is a straight line passing through origin, because it is like y equal to mx. Y equal to mx, and this slope is equal to kh, and that is measured in bar or atmosphere, right? So this part is also important. This indicates the validity of Henry's law. Now, so if we consider the common formula for Henry's law, that is PA equal to KH XA, then KH value is different for different gases. So higher is the value of KH, lower is the solubility at a given pressure. Because see, if pressure is constant, partial pressure of any gas is constant, then KH into XA. If KH is higher, then XA is lower. What is XA? Mole fraction of the gas in the liquid, in the solution. That means it is actually solubility. So if KH is higher, solubility is lower. So any gas having higher KH value has a lower solubility, and KH should be measured in bar or atmosphere. Keep in mind, if it is per bar or per atmosphere, then relation is inverse. Okay. Second thing, as temperature increases, what happens? What is the effect of temperature on the value of kH? If temperature increases, you know what is the effect on solubility? Solubility of a gas in a liquid decreases, and that's why value of kH increases. So when we increase the temperature, kH will also increase. Okay, but keep in mind, if kH is in bar or atmosphere, if it is per bar or per atmosphere, then both the equations changed. Okay, now limitation. As I discussed, what are the limitations of Henry's law? So Henry's law is applicable only if pressure should be low, or we can say pressure should not be too high. It should be low, and temperature should be high, or we can say temperature should not be too low. That means gas should behave like an ideal gas. That is the first condition, that pressure at which we measure the solubility should be low and temperature should be high, so that gas behaves ideally. And second thing, gas should not associate or dissociate in the given liquid, or should not combine with solvent. Right? These are the two conditions that should be met by the gas to be followed by Henry's law. If these two conditions are not satisfied, Henry's law is not applicable. For example, for HCl and ammonia, you know, these two gases are sparingly soluble in benzene. So for HCl and ammonia in benzene, Henry's law is applicable. But if we dissolve these gases in water, then Henry's law is not applicable for them, because when HCl is dissolved in water, what happened? It dissociates into HCO plus and Cl negative. That's why for the solubility of HCl in water, Henry's law is not applicable. Very important question for competitive exams. Keep in mind. Second is ammonia gas. When we dissolve it in water, first it leads to the formation of compound followed by dissociation. Again, Henry's law is not applicable. Right? That means gas should not be highly soluble in the given solvent. Gas should be sparingly soluble, so that we can see the effect of pressure on its solubility. So these are the limitations of Henry's law. And what is the effect of temperature on KH, or nature of gas also affect KH. For example, if we have O2, N2 and helium. So you know, we have discussed it in the nature of gas that O2 is more soluble. If we consider solubility, then O2 is more soluble than N2, which in turn more soluble than helium. So what about KH? So as solubility is more, KH is less, or if solubility decreases, KH increases. That means KH of helium is maximum and O2 is minimum. So order of value of KH is like this. This is about solubility and this is what their KH values. So value of KH depends on nature of the gas as well as on the temperature and even on the units. Here we consider KH unit as bar or atmosphere. Repeatedly I talk about units of KH, units of KH, units of KH, because that is very important. Because when we have unit of KH, we can decide which relation of Henry's law is used for the calculation. Okay, now we will discuss the application of Henry's law. Okay, just note down. Now let us discuss the applications of Henry's law. So first application is in the production of carbonated beverages, or we can say drinks like soft drinks, even soda bottles, beers, champagnes. So to increase the solubility of CO2 in these bottles, they are stoppered at high pressure. Means that bottle is closed, that cap is closed under high pressure, right? So that is the application of Henry's law, because when pressure is increased, solubility increases. So we can say to increase the solubility of CO2, bottles are sealed under high pressure. So this is the first application. Clear? And when we open the bottle, what happened? Now again gas is under atmospheric pressure, so that gas bubbles out because pressure is reduced, and that's why solubility decreases. Okay. The second application is in deep sea divers, scuba divers. In deep sea, that is called scuba divers. So what they do, they took, or we can say they take tank of gas with them to breathe. Now if that tank contains normal air, so you know under atmospheric pressure O2 is dissolved in the blood and fluid, body fluid, but N2 is insoluble under atmospheric pressure. But when it goes deep inside, what happened? Pressure increases, so the solubility increases. That's why O2 as well as N2 both are soluble in the blood and body fluids. So what would happen? O2 is used in metabolic processes. O2 is used, but N2 remains insoluble in the blood. So as long as it is in the deep sea, then N2 is soluble, But when it comes under atmospheric pressure, what happened? Solubility of N2 is low now. So N2 becomes insoluble, and in the form of bubbles, it tries to come out, and that's why it blocks the capillaries. And a medical condition known as bends or decompression sickness is developed, and that is very dangerous to life. It is life threatening. So in order to avoid bends, or we can say decompression sickness, that tank containing air is diluted with helium, because helium is insoluble in water, even at insoluble in the body fluid or blood, even at high pressure. That's why the tank which scuba divers carry with them has 11.7% helium, 56.2% nitrogen, and 32.1% O2. So now when partial pressure of nitrogen is reduced, now N2 is not soluble in the blood even at a high pressure, because partial pressure of the gas is directly proportional to mole fraction of the gas in the solution. Okay, so we can avoid bends by using this diluted air. This is the second definition, second application. Now third application is at high altitude. Third application is regarding at high altitude. What happened? Atmospheric pressure is low, so is the partial pressure of oxygen. So oxygen intake by the person staying at high altitude is low, and that's why a person become weak and is unable to think clearly. A symptom known as a medical condition, or we can say anoxia symptoms, are developed in that person. So keep in mind, these are the three applications of Henry's law. First is in the production of carbonated drinks, we seal the bottles under high pressure so that more CO2 is soluble in the liquid. And second is in the tank carried by scuba divers. In that tank, if we carry the normal air, then there is a medical condition, that is bends are formed, or we can say decompression sickness is developed in the person, and that is dangerous to life. It can block the capillaries, okay, because bubbles, if the gas comes out in the form, try to come out in the form of bubbles. And third is high altitude sickness. It is also called high altitude sickness, and the medical name given is anoxia, because in that case, when oxygen intake by a person is low, means oxygen is less soluble in the blood, then person becomes weak and is unable to think clearly, right? So these are the applications of Henry's law. Thank you very much for watching this video. Do like, subscribe and share my channel. God bless you all. Happy